All right, this is your last big convergence test. This is the ratio test. It's my favorite. You can use the ratio test to determine whether a series converges or diverges, just like everything else we've done so far this chapter. After the ratio test, we're going to start moving on to other ideas this chapter. All right. The ratio test is great at getting rid of factorials and exponentials. So the ratio test says, suppose you have a series with positive terms, and if you take the next term divided by the previous term and do the limit as n goes to infinity, you get a number. If that number is less than 1, including 0, then the series converges. If that number is greater than 1, including infinity, then the series diverges. If your limit is equal to 1, your test didn't work, and then you're unhappy because you have to use a different test. All right, so here we go. If I look at this one, it looks almost geometric, but not quite because it has that extra n in it. So I'm going to go ahead and set up the ratio test. So it's going to be n plus 1 times 3 to the n plus 1 divided by 10 to the n plus 1, and then all of that divided by n times 3 to the n over 10 to the n. And I'm going to simplify by by multiplying by the reciprocal is what I'm going to do. And with exponents, if you have the same base and you're dividing, you can subtract exponents. So with these 3's, I can subtract exponents, and I would wind up with 3 to the 1 power. And with the 10's, I can subtract exponents, but they're going to wind up in the denominator, so I have a 10th. And then I also have n plus 1 over n. Well, if n is going to infinity, right now this is infinity over infinity, but the end behavior would be n over n, so this part would go to 1. And so our limit is going to be 3/10. 3/10 is less than 1, so the series converges by the ratio test. Nice thing about the ratio test is you don't have to do a comparison, so you don't have to have another series that you know anything about. You just have your one series, and you're kind of comparing it to itself. You're comparing its next term to its current term. All right, so this is done. We've got that the series converges by the ratio test. All right, here's one with a factorial. I promised you that factorials would go away, so we're going to go ahead and do that. We'll do the limit as n goes to infinity of n plus 1 factorial over 5 to the n plus 1. And if it's okay with you, I'm just going to multiply by the reciprocal right now. I'm dividing by this, so I'm multiplying by the reciprocal. And then the reason that factorial goes away is because what factorial means is it means n plus 1 times n minus 1, etc. until we get to 1. And this would be 5 in the denominator, because we subtract the exponents. And then n factorial would be n, oh, I want parentheses around that, n minus 1, times n minus 1, etc., until we get to 1. And what I notice is that this and this can divide to make 1, and so I'm left with the limit as n goes to infinity of n plus 1 over 5. Well, if n is going to infinity, then this limit would be infinite, and so our series diverges by the ratio test. We got a number larger than 1 for our limit, so our series diverges by the ratio test. All right, here's one we're going to try the ratio test again, so we'll do the limit as n goes to infinity. I'm going to multiply by the reciprocal again, which is just n squared plus 1. And then I'm going to think end behavior because I'm going to infinity. So the end behavior would be n squared over n squared. And this is when I get sad because the ratio test doesn't work. We can't use the ratio test, so we're going to use a different test. I'm going to compare it to 1 over n squared, which diverges. Lied. It converges because it's a p-series with p equals 2. So since it's a p-series with p equal to 2, it converges. And every single term of our series is a little bit smaller than every single term of 1 over n squared. So by direct comparison, our series converges. So that's this is kind of the wrinkle about the ratio test. We can try it for every single series, but it's not always going to work. Sometimes we're going to get a number of 1, and if our limit is 1, then we can't conclude anything from the ratio test. Well, here's one that looks promising because it has factorial in it. I'd recommend that you start it off on your own, see if you can make this work for yourself, and then come back and try and see my solution after you're done. If you tried it, make sure that you're replacing the n with an n plus 1, so that's going to get more complicated than just having a plus 1 at the end because of that 2. I'm going to multiply by the reciprocal. So n plus 1 times n factorial, and this would be 2n plus 2 minus 1, so 2n plus 1 factorial. And then this would be 2n minus 1 factorial over n factorial. So the n factorials are going to cancel away, and then I'm going to look at these 2n minus 1 factorial. I'm going to leave that alone. And I also have an n plus 1 in the numerator. And so then I have 2n plus 1 times 2n times 2n minus 1 factorial. And so my 2n minus 1 factorials go away. And now if I look at dominant terms, I would have n over 4n squared for dominant terms. And as n goes to infinity, this would be 0. And so our series converges by the ratio test. All right, that is the ratio test. It's a little bit like a comparison test, except you're comparing a series of the next term to the previous term, and you are looking at that limit. Remember that if you get a limit of 1, it's a bummer. You don't get to use the ratio test. All right, good luck, have fun.